So today we are here to solve the daily Leetcode challenge for the day, flip equivalent binary trees. Okay, so this problem is about binary trees, and in order to understand this problem, first of all we have to go through the problem statement. So let's do that. So in this problem we are given this binary tree, okay, and it is asked, the problem heading itself says flip equivalent binary trees. Okay, so the heading itself says flip equivalent binary trees. Okay, and what is this flip operation? So in the problem statement it is mentioned flip operation is as follows. Okay, choose any node. Okay, we can choose any node, either the root node or this node or the leaf node, anything. Okay, it is not mentioned here which node. Okay, choose any node and swap the left and right child subtrees. Okay, so it is saying that flip operation consists of swapping the left and right child subtrees. So let's say suppose we are considering this root node and 3 is the left child and 2 is the right child. Okay, so if we swap 2, 3 and 2, then we'll get something like this. 2 will come on the left side and 3 will go to the right side. For this tree, for the tree on the right hand side, if you swap the first level children's, 2 will come on the left side and 3 will go to the right side. And see, and this flip is, and the second thing it is mentioned in this problem statement is that a binary tree X is flip equivalent to a binary tree Y. Okay, so two trees are considered equivalent, okay, if and only if. So when we can make X equal to Y after some number of flip operations. Okay, so it is mentioned, see, if we can make X equal to Y, okay, after some number of flip operations. It is not mentioned how many numbers, either it could be 0, it could be 1, it could be 2, it could be 3, howsoever number of howso many number of flip operations are required, perform them, and if after doing it two trees are equal to one another, then those trees are flip equivalent. So this is just a binary tree and flip is just swapping the left and right child. So this is not a very big thing. I mean to say, if it is an array tree, then the flipping would have been little complex, but here it is easy. And now the problem asks us to, if we are given the roots of two binary trees, root 1 and root 2, then return true if the two trees are flip equivalent or false otherwise. Okay, please return true if two trees are flip equivalent or false otherwise. Okay, so how can we do that? Okay, how can we do that? So since this is a binary tree, okay, and only thing is here that we need to swap the left and right child. Okay, so see, if we swap the left child and right child, then it becomes this, like this. But if you swap them again, then it comes back to this. So either it could be swapped one time or it could it could not be swapped at all. Okay, so there are only swapping has only two effects, either it could be swapped or it is not swapped at all, because if you are after swapping it once, if you are swapping it once more, then it comes back to its original form. This is the very key thing about this problem, like all even numbers are the same and all odd numbers are the same. It is that kind of thing, because this is a binary tree, and if you are doing swap once and after that we are performing the swap one more time, then it comes back to its original form. Okay, so it is just like saying that all even numbers are the same and all odd numbers are the same. So just we have to check whether it is swapped or it is unswapped. That is the only thing we have to check. And how to check that? Okay, so to check that, first of all, let's say if the given roots are null, if the root 1 is equal to null, okay, see, in the problem parameters find equivalent, we are given two roots, so we can check whether the two roots are null. And okay, root 2 is equal to null. So since these two both are null, then we can imagine, see, suppose nothing is there, and if we are swapping nothing, then also the result of that swapping will be nothing is swapped, so nothing will be remaining, and nothing is there, and those two nothings are equal, so we can return true. But if something is contained over there, okay, let's say root 1 is not null, root 1 is equal to null, okay, or root 2 is equal to null, okay. So see this line number 18, now after this line, nothing which the situation that the two roots are null cannot occur, okay. So we can the two roots are null cannot occur. Why? Because we are returning true at the line number 18. If the two roots are null, both the roots are null, then we are returning. But if you are coming to line number 18, and even then let's say root 1 is null, then it means root 2 is not null. And if root 1 is not null and root 2 is null, then in that case we can return false. Pretty much obvious, okay. There is nothing on one side, but there is something on the other side, so nothing and something cannot be equivalent, okay, definitely. So we can return false. But now the thing is, after this line number 19, the thing is that what is remaining here is that root 1 value can be, its value can be different. So if it is different, okay, then we can say root 2.val, then also we can return false, okay. So this is very important condition. Now how to check that the order, the roots, how should we be checking the for the sub cases. So now we have, if these two this node here and this node here, okay, for these two nodes we have all the conditions in line number 18, 19, 20 are sufficient to check the two nodes here, the topmost nodes here. But how to check the lower level things? To check the lower level things, remember I had told you that if we have swapped this one, left child goes to the right child. So once left child here is becoming the right child. So in that case, we can check the equivalence like find equivalence like root 1 dot left and root 2 dot right, either if it is swapped. So here whatever is the left child is becoming the right child, and find equivalence of root 1 dot right. So what was the right here? 3 is on the right, and that 3 has become left here. So this is root 2 dot left. Perfect. Okay, so this is one situation, and I told you that if this tree is swapped once and then again it is swapped back, so that condition is also there. To check that condition, what we need to do here, that we can do one OR, okay, and simply we can do this find equivalent. So in this case, the left of the two are, after swapping we are doing one more swap, so it remains unswapped, okay. Ultimately, eventually it remains unswapped. So root 2 dot left is also equal to the root, these two nodes are equivalent. Either the swapped things are equivalent or the unswapped things are equivalent. If these two conditions are there, only these two conditions can be there, okay. It cannot be anything else. Okay, so we have to put here root 1 dot left, root 2 dot left, root 2 dot left, and here also root 1 dot left, root 2 dot, no, left is already checked, so root 1 dot right, and here also root 2 dot right. If this is there, and then we have to do return like this, like this. Like this. So this is all, that's all we need to do. See, for the given root, these three conditions are concerned only with the given root. Okay, the roots 1 and the root 1 and root 2. So these three conditions are only concerned with the two root nodes that we have been given. Okay, other than that, whatever work is being done, that is done by the recursive formulation of our problem, and that is doing the work for us. We are only handling the base case, the ultimate base case. Apart from that, nothing we have done. And let me run this and show it to you whether it is succeeding or not. Okay. So root 1 is equal to null. This is root 1. Okay, some spelling mistakes are there. Find find not, it's flip equivalent. Okay. Oh, there is one more flip equivalent. Okay. So I have to be little careful. This is the problem when we start recording late in the night. Perfect. Now I'll submit this. Perfect. So this is the solution that I wanted to share with one and all. Happy coding, best wishes.